So hello again. On the previous slide here, um, um, so I started speaking about the Soderberg equation. So remember, this is Soderberg failure line, and how we can just get the equation based on similar triangles. Eventually, we've just simplified this equation to get the factor of safety equation. So based on Soderberg, the factor of safety is equal to the yield strength of the material over the mean stress plus the fatigue stress concentration factor multiplied by this ratio, S yield over the endurance strength multiplied by the reversed stress of the material that is applied on the material. So the factor of safety that you're getting here, normally in statically loaded components, we were looking for a factor of safety that is higher than 1, normally in the range of 3 to 4, something like that. Here, in this case, if the factor of safety is unity, so it just means that the material or the component can survive forever or can have an infinite life. So normally when you when you design your shaft, you will start by the static loadings first, as we've learned before. And then here, when it comes to fatigue loading, you can just check the factor of safety. So the only step that you need to do here, maybe it's going to be to find the factor of safety based on the fatigue loading on your shaft. And if the factor of safety here is higher than 1 or greater than 1, or equal to or greater than 1, it means that it have infinite life. Okay, so this is a quite important step in your design. So in practice, you will have this factor of safety value is between 1 to 2. So you will see that the stresses applied on your component can take any form. It can be direct tension, for example, or compression. Okay. In this case, we are going to take this equation. Remember the name, the number of the equation. This equation number 9. This is our first equation based on Soderberg failure line. So we're going to take this equation, and depending on the type of the stress that is applied on the component, we're going to just tweak this equation a little bit. So first, if you have a direct tension on the component, so the sigma value or the stress or the direct stress is equal to the force divided by area, where F is the force and A is the cross-sectional area. So if we take that equation number 9 and then multiply the right and the left-hand sides of this equation, sorry, the right-hand side of the equation, top and bottom, or denominator and numerator, by the cross-sectional area. So let me just go back here. So we'll take the right-hand side of this equation, and then we are going to multiply the top by the cross-sectional area and the bottom by cross-sectional area. So at the top here, we'll have S yield times the area, but here we have sigma mean times the area for the first expression, and sigma r times the area for the second one. So sigma mean times the area is equal to F mean, and sigma r times the area is equal to Fr. So in this case, if we have the mean force and the reversed force, we can just simply use them into this equation instead of the mean and the reversed stresses. That's why we have F mean here and Fr, where F mean is the mean force and Fr is the reversed force. This makes it easier. And also, this just adds this area here where you can rearrange this equation so that you can, if you wanted to find the area or the cross-sectional area, or you want to design your component based on fatigue, so you can just find the cross-sectional area based on this equation, if the factor of safety is assumed or known or given. Okay. The second thing, if we have reversed bending, remember the reversed bending? Fully reversed bending means that you have the time here on the x-axis, and on the y-axis you have sigma, and then you have a fully reversed loading here. So it means that the value, sorry, it didn't say fully reversed here. I just made this up, I think. So if the time is here, so, and the mean value is here, so, and we have a reversed bending, something like this. This is the top one is a special case where we have fully reversed, where the sigma mean is equal to 0. We'll see this in a moment, but it's not the case. So let me just get rid of this at all. So we have a reversed bending here. So the idea is that sigma bending, based on what we've learned before, is the moment times the second moment of area. So the moment times y divided by the second moment of area. So what we need to do here, we need to go back again to equation number 9, and then if we multiply the numerator and the denominator of equation number 9 by I over y, so this will just convert somehow these stresses to bending moments. So you see here, for example, if you have sigma bending, as I said, is equal to m times y over I, okay? So if you multiply the left and the right hand sides by I over y, so you have here I over y on the left hand side times sigma bending is equal to m. So if this bending moment is mean, the mean value, so this gives you the mean value of the bending moment. If this value here on the left hand side is the reversed bending stress, so this gives you the reversed bending moment. And this is what exactly what happens here. So you multiply the top and the bottom of this equation number 9 by I over y, and the mean stress is becomes the mean bending moment, and the reversed stress becomes the reversed bending moment. This makes it even easier. And also, again, you can here you have this I over y, because I over y is function of the geometry. For example, if you have a solid circular cross-section with a diameter d, so in this case, the second moment of area is pi times d to the power 4 over 64. And the y value here, if we have bending moment, so the y value is equal to d over 2. So here again, if you want to rearrange this equation so that you can find the diameter of the component, you can do so. The next one is fluctuating torque. So it is similar to the bending moment, but here we have tau versus time. So we have here the shear stress due to torsion versus time. And again, we could have here something like this. If this is the mean value of the shear stress, and this is the fluctuating or the reversed shear stress. So from here to here is tau mean, which is the mean shear stress, and between the top point here to the this line, we have tau r, which is the reversed shear stress. So in this case, we are going to again go back to equation number 9. And if you remember, tau is equal to the torque times r over j. So we'll need this in a moment, maybe on the next slide. But what we need to do here is that we need to consider that we have a factor of safety, but we're going to call it like factor of safety for shear or in shear. And then here we have the S yield in shear, and we have the endurance strength in shear. And this is quite important. Let me just go back here to emphasize this. So in the case of direct tension, okay? So we have here S yield, okay? The endurance strength. This endurance strength in the tension should be measured from a test that is based on tension, not bending. So we have a force here, and then this force changes from maximum to minimum, and then we should have something similar to the experiment that is done by Wooler, so that we can have the endurance strength in tension. Here in bending, we can use the SE value that is calculated or measured from the Wooler test. And here in torque, we have S yield in shear, where the S yield in shear is the endurance strength of the material in shear that has to be found somehow. One way of doing that is for ductile materials. They have found, based on, again, experiments, lots of experiments in fatigue, they have found that the endurance strength in shear is equal to 0.5 times the endurance strength based on the bending, or that is found from Wooler test. So if you have the endurance strength that is from Wooler test, multiply this by 0.5, and this gives you the endurance strength in shear. The same applies for the S yield, because here we have S yield in shear. So if you multiply the yield strength of the material that is found from the simple tension test by 0.5, this gives you the yield strength in shear. So this is quite important even to remember. Then I was talking about this on the previous slide. I said the shear stress due to torsion is equal to the torque multiplied by R over J. And if we have a solid cross-section, a circular cross-section, where you have, this is the radius R. So if you multiply here this equation that I wrote, the left and right hand sides by J over R, so you have J divided by R times tau is equal to the torque. And this is exactly what we want. We're gonna take equation number 9 back again to equation number 9, multiply the right-hand side of the equation, the top and the bottom, by J over R, and then eventually, instead of the tau R and tau mean, we're gonna have T mean and TR, where T here means the torque. So in this case, Tm is the mean torque, and T sub R is the reverse torque. But on the previous slide, you see here, we have tau mean and we have tau R, but this is before we multiply the top and the bottom equation by this factor J over R. So this factor J over R is based on the geometry again, where J actually is pi over 32 times the diameter to the power 4. This is for a solid circular cross-section, and then multiplied by, this is 2 over D, because this R here is D over 2. If you just get this, the reversal of this, it's 2 over D. So in this case, we can use this equation to find the factor of safety in shear for this case, which is fluctuating torque. What if we have combination between like kind of bending and torsion, which is going to be the case in our shaft? So in this case, the analysis started by the maximum shear stress. What is the maximum shear stress of this material? It is tau max is sigma over 2 squared. I think there is a mistake here. So it's sigma over 2 squared plus tau squared, where sigma here is the bending stress and tau is the shear stress. And based on the MSST, which is the maximum shear stress theory, we can say the factor of safety is equal to the yield strength in shear divided by the maximum shear stress. And the maximum, again, this is squared here. So the maximum shear stress is the square root of sigma over 2 squared, which is like for bending stress, plus tau squared, which is the shear stress. in this case, they have just tweaked the equation a little bit to apply the fatigue or to include the fatigue analysis. They said what we can do here, we can consider that sigma, okay, is equal to two components. The first component is the mean value plus another component, which is the reversed value. But we are going to multiply this reversed value by just some sort of a ratio. And this ratio is the S yield over SE. Okay, so this becomes now the, if we were to consider the fatigue, the mean value and the reversed value, so we can just substitute this sigma value back into this equation, which is equation number 17. But we have to do the same with tau as well. So they have considered that tau, again, is equal to two components, the two superimposed component. One is the mean value of the torque plus the reversed value of the torque that is multiplied by S yield in shear over the endurance strength in shear. So now we can take these two values or these two equations. Of course, they made it sigma over 2 squared and tau squared, because if you go back here, you find that it is the square root of sigma over 2 squared plus tau squared. So we can just substitute these two equations, 18 and 19 into 17, then eventually we will get this equation. So the factor of safety in this case, if you have a combined load, is equal to the yield strength and shear over this long bracket here. So what if you have a completely reversed bending, the one that I was talking about in just a moment? So completely reversed bending means that it just fluctuates between the x-axis. So sigma maximum and sigma minimum are equal and opposite in sign. And then you have a steady torque, because the torque does not change with time. So the torque, in this case, the torque with time just is kind of steady. In this case, the reverse torque is 0. So this part goes to 0. And because we have here completely reversed bending, sigma bending, so it means that the mean value of the bending is 0 as well. So this just simplifies to this equation. So this equation can be used if you have a uniform torque or a steady torque and you have a completely reversed bending. So you can use this equation to find the factor of safety of your shaft, okay? As I said earlier, if you remember, so the endurance strength of the material is not like an inherent property of the material. There are lots of things that affect the endurance strength, okay? So in this case, we should consider the factors that affect this fatigue strength. And eventually we come up with a modified value of the endurance strength or the fatigue strength. So it's going to be SE prime, which is equal to the SE value that is being measured, multiplied by some factors here. So we need to think of or just to go through these factors. One of the most important factors that affect the fatigue strength or fatigue resistance is the surface finish. So depending on the surface finish of the specimen that you are testing, so its endurance strength can be affected. In this graph here, what you see polished specimen, you have ground specimen, you have machined specimen, you have hot rolled specimen, you have forged specimen, okay? So it just means that if you just draw a vertical line here, okay, it's not very vertical, so so if you draw a vertical line here, semi-vertical, So it means that we are picking one of these materials. So if the material has this kind of ultimate strength, so in this case, you have a specimen from this material is forged, another specimen that has hot rolled, and then another specimen that is with a machined surface, another specimen with a ground surface, another specimen with a polished surface. So for all these specimens, they do have the same kind of geometry, but the surface finish changes. You see here, for the polished specimen, the surface factor that we're going to call K sub A is equal to 1. So this is kind of the value. If you multiply, again, back here, if you multiply this value by 1, so it's not effective. It means that for polished specimen, this is kind of the standard or the reference case for us. For the ground, it's going to be a little bit less. So let's say 0.9. So, and if it is machined, so it's going to be 0.7, hot rolled, it's going to be 0.5, forged, it's going to be 0.3. So you are going to multiply this value that is measured from the experiment by one of these factors, depending on how your specimen or your component is made. And this will just reduce this value. Because, for example, if you multiply by Ka here, and this Ka is 0.8. So it means that your value that you are going to use in those equations that you have seen is equal to the value that you get from the textbook or the experiment multiplied by this value, depending on the surface finish. And if this value is 0.5, for example, so you are getting only 1/2 of the value that, or you are considering only 1/2 of the value that you get from the experiment. Okay. Another effect is the size effect. So we said that the standard specimen, the minimum diameter in the standard specimen is 7.5 mil. So what if you change the diameter? You see here, the diameter changes from 0.7, no, sorry, this is for the vertical axis. So it's 10 mil, it's 20 mil. So here it should be 7 mil, which is kind of the standard value, 30 and so on. So when you increase the size of the specimen, so the value, the strength of the material, or the endurance strength of the material goes down. So when the diameter is 7.5 mil, so the size factor is around 1. But when you increase the size, so the material becomes weaker. So in this case, the probability of the material having more just defects is more, and then consequently its endurance strength becomes more. So the size factor is called K sub B in this case, and it can be found using one of these two equations. The size factor is equal to 1 if the diameter of the specimen, or the minimum diameter of the specimen, is less than or equal to 8, and can be found using this equation if the diameter is higher than 8 and lower than 250. So one thing I forgot to say here is that based on this, this graph is for steel, for the surface finish, and based on the range here, you see the Ka, which is the surface finish factor, varies between almost 0.2 to 1. So the third thing is the reliability. Okay, so if you look at the curve here, you will find that all these dots, they go around the curve in the middle. Okay, so normally the experiment give us some results that are scattered. So there is a band, scatter band. It's not like you connect all these dots or these results and then they give you a nice and smooth curve. So they are scattered, and then consequently they use a curve that goes in the middle of all these points. It means that we have here a 50% probability of survival, because the line that we use for our calculations is in the kind of in the middle of all these scatter band. So we here have to consider the reliability of our values here of the SE, or the endurance strength. You see here this little graph here. It shows the normal distribution of the values that we get based on experiments. And then they've suggested that a standard deviation of 8% of the endurance strength is employed for calculations. So first, having this line in the middle of the band, okay, means that the published data represents only 50% probability of survival. So the accurate life, or the finding the accurate value for endurance strength, is quite challenging, honestly. So that's why they employ this statistical procedure or calculations or analysis to consider this, or to take this into account. So the table that you see here gives you, on the right-hand side, gives you something called reliability factors. So the reliability factor here is considered based on this table. So if you have 0.5 reliability, so this means that the reliability factor is 1. Because going back here, as we said, so we consider the line in the middle. So by considering the line in the middle, or considering the mean data here, so we have 50% probability of survival, which is like, if the probability of survival here, or the reliability, is 0.5, which is equivalent to 50%. So we don't need to modify or reduce the value of the endurance strength. But if we wanted more kind of reliability or survival rate, it means that we have to reduce the value of, or modify the value of, the endurance strength. So for example, if you want your data to be almost 100% reliable, so this means that the value that you are getting from the experiment, you need to modify it by almost 50%. So you need to multiply this SE value by almost by 0.5, which is almost taking only half of this value. This equation here can be used to calculate the reliability factor based on what we have here called the standardized variable. So you see what reliability factor or survival rate are you aiming for, and based on that you find this standardized variable, and consequently you can find the reliability factor that you are gonna multiply by the endurance strength, or you can use this equation again based on the table. And here you see the endurance strength of the material corresponds to nearly 100% reliability, means that only about half of the tested value can be used. Another factor is the temperature. You know that when you test those specimens in the lab, so you have a specific temperature, but when the component is used in real life, so there are other temperatures that can affect the material. Consequently, we have to consider this type of or this effect and take it into account. So for elevated temperatures, so that we can use what's called the temperature factor, K sub D. And for steels, if the material of the component is made of steel, so the temperature factor is 1 if the temperature is less than or equal to 450 degrees C. And we can use this equation to calculate the temperature factor if the temperature is between 450 and 550. Again, if you remember, we were talking about the fatigue stress concentration factor, which is K sub F, or the modified factor of the theoretical stress concentration factor. Here, they want to simplify the calculations. If you want, nothing is new here apart from we can consider that we have another factor here. We call it the stress concentration modifying factor K sub E, which is 1 over Kf. But this means that because this is going to be, you know, we have left-hand side of the equation, and then we have right-hand side. The right-hand side includes the endurance strength. So if you were to multiply the endurance strength of the material by 1 over Kf, it means that you cancel the Kf here. So let me just go back here. If I go back to the equation, it might be easier and straightforward. Just look at this equation, Soderberg equation that we are going to use, okay? So for this value, we're just trying to find all the factors to modify this value. Just consider that you multiply here by 1 over Kf. So you have to multiply the second or the left-hand side of the equation by 1 over Kf for only this factor. So this Kf cancels with this Kf, and then this value here or this factor here is the one that we are talking about. So in this case, if you multiply the endurance strength by this factor Ke, so you don't need to use the Kf on the left-hand side, you use it on the right-hand side, or it is included in the calculations of the endurance strength, okay? Also, we have what's called miscellaneous effects, other effects, any other effects, because there are other effects that can modify the value of the endurance strength. Something similar to residual stresses, for example, after some manufacturing processes, or similar to cold rolling and so on. If we have internal defects in the material that we don't see and we didn't take into account, if we use the material in a corrosive environment, or if there are any other like manufacturing processes applied to the component, like plating, for example, or due to the movement between some surfaces, there are some wear between them. So all these will be combined together in one factor called miscellaneous effect or miscellaneous factor. So there is an example here, and of course there are other values in literature, or you can search for them and in the textbooks. And here one example of fretting or wear between mating ports is called Km, which is again the miscellaneous factor. If we were focusing only on fretting, so this is going to be between 0.24 to 0.9, depending on the materials of the mating surfaces. Eventually, we're almost there, guys. Last slide. So in this case, you see here, this is the value that we measure from the test. And these are all the factors that we need to take into account, like surface factor, size factor, reliability factor, temperature factor, and this 1 over Kf, which is the notch sensitivity, and also the miscellaneous factors. So the value that you get from the experiment or from textbooks, you need to multiply by different values to get what's called working endurance strength. And this working endurance strength is E prime. This is the value that you are going to use in equation number 9. And is it 21? Let me just check. For the, 20, no, I think 21 for the combined stresses. Yes, these two equations that you use if you have combined loading, and equation number 9, which is the kind of the first equation in this analysis, which is this one that you use for direct stresses, for reverse bending, reverse torsion, and so on. So eventually, before you use the SE value in equation number 9 or any other equation that derived from that, or the equation 21 that is used for combined loading, you need to modify your endurance strength value that you get from textbook or from the experiment. And that's it.